So let's say I was less nice. Instead of writing it this way, I just said, find the following. I just want to point out, if you see on a test or somewhere, find the derivative of something to a power, and both the power and the something have the variable x, or whatever the variable is, you need to take the additional step of writing it as y equal to something so that you can take the natural log of both sides. You can't just take the natural log of it unless we have y on the other side to take the natural log of as well. So we need that y there so that we can take the natural log of both sides. The natural log of y is equal to the natural log of x plus, whoops, plus sine of x, not 3x. Sorry, let me write it again. Apologies. Natural log of y is equal to the natural log of, thank you, natural log of, thank you, natural log of x plus sine of x to the 3x power. And of course, the whole benefit of taking the natural log of both sides is that we get to bring that power down. So we're going to rewrite this as the natural log of y equal to 3x times the natural log of x plus sine of x. For those of you just coming in on Zoom, here's the attendance form in case you need it. Also, for those of you here, please fill out the attendance form, which is on the QR code as usual. So, where was I? I was doing the problem. So then we're going to differentiate both sides. The derivative of the natural log of y is always going to be 1 over y times y prime. Or as I like to say, right, the derivative of the natural log of some stuff. So 1 over the stuff times the derivative of the stuff. On the right-hand side, got to be a little bit more involved here. It's going to take the product rule. So I'm going to do the derivative of 3x, just 3, times the not derivative of the other stuff, which is natural log of x plus sine of x. Plus, then we flip it around, right? We leave the 3x alone. And we multiply by the derivative of the natural log of x plus sine of x. So again, I've got the natural log of some stuff. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of that stuff, which is 1 plus cosine of x. Nothing's going to cancel or simplify there. You might be like, can we cancel an x there, an x there? No, we can't. Right? You have to factor out an x, which we can't. Factor out an x on the bottom. So we're just going to simplify. And I really recommend, if you're short on time, right? I think it's perfectly fine to do this next thing in one step. I'm going to multiply both sides by y. I'm also going to replace y with what y is actually equal to, which is x plus sine of x to the 3x. So I'm going to get y prime equal to y, which is x plus sine of x to the 3x. There's my y, times all of this stuff here. 3 times natural log of x plus sine of x. Plus, you might simplify this a bit. I don't think the only simplifying I really want to do is write it as 3x times 1 plus cosine x all over x plus sine of x. That's kind of it. And that would be your answer to this particular derivative. Or I should say, this would be the derivative of x plus sine of x to the 3x. Observation: whenever you're differentiating something with a variable in the exponent, the original expression always pops up exactly as it was, right? We're always getting that original thing and then multiplied by some other stuff. Sometimes it's very basic, right? Like when you take the derivative of 2 to the x and you get 2 to the x times natural log of 2. Sometimes it's a little more complicated, like when you differentiate 6 to the x cubed plus tangent of x, and you get 6 to the x cubed plus tangent of x times the derivative of the stuff times the natural log of the base. But still, the original expression is totally popping back up. And that's always true when your derivative has a variable in the exponent. It's kind of neat. Questions about either of these two things here? No.
Is it possible if we try to get the derivative of x or whatever is in parentheses, can you do the natural log or is it just that
You can. So you definitely could if you wanted to. For anything where you've got variables in the exponent, you can use a logarithmic differentiation. So if you wanted to, for the derivative of 6 to the stuff, we could totally write it as y equal to 6 to the stuff. And then take the natural log of both sides. Natural log of y is equal to the natural log of 6 to the x cubed plus tangent of x. We bring the power down in front. That's the whole reason for taking the logarithm. We get the natural log of y equal to x cubed plus tangent of x times the natural log of 6. We differentiate both sides. And the difference here is that when you differentiate the right-hand side, we no longer have to use the product rule like we did in our previous example. Because in our previous example, we had our exponent times the natural log of our base, and both of those had variables in them. But now, our exponent times the natural log of our base, the natural log of our base is just a constant. So this is just a constant here. So the derivative of the right-hand side is just going to be 3x squared plus secant squared x. I should say secant squared of x times natural log of 6. That's it. And you solve for y prime the same way you bring y over. And I suppose I could skip this step. And then you get y prime equal to the original y, which is 6 to the x cubed plus tangent of x times 3x squared plus secant squared of x times natural log of 6. Yeah, you can totally do it that way. The thing I'll say about this is that generally it's thought of as perfectly fine to memorize the formula for when you have a base to a complicated power. So we know the following kind of rules. We know the derivative of e to the x is e to the x. We know the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And then if you make the base something other than e, you're just going to introduce a multiple of the natural log of that base. So the derivative of something other than e to the x power, like b to the x, is b to the x times the natural log of b. And the derivative of b to the stuff is b to the stuff times the derivative of the stuff times the natural log of b. But it's perfectly fine to do it this longer way. It's just usually okay to be like, I know the formula for the derivative of 6 to the stuff. It's 6 to the stuff times the derivative of the stuff times the natural log of 6. One sec. On the other hand, if your base has variables in it and your exponent has variables in it, that's when you really absolutely have to use the logarithmic differentiation. But it's perfectly fine to use it here if you prefer to. Yeah.
So is that why e to the x is e to the x, because the natural log of e is just
Right. This formula totally works for e to the x. The derivative of e to the x is e to the x times the natural log of e. We just don't write the natural log of e because it's equal to 1. So this is, yeah. So this is really the formula you can always remember. It's just that for e, we don't really need it. Yeah. Okay. Other questions about this? Yeah, Kate.
The first problem is,
This one here. It was lengthy. Other questions? Okay. So, yeah. So I remind you all of how would I say this? So I don't remember which way we did this. When we learned how to take the derivative of the natural log of x, I think we did it as like an inverse function kind of thing, right? I think, let me remind / ask you all. When I was doing before, I think we did this. We found the derivative of the natural log of x by saying, well, we're going to write y equals natural log of x. We're then going to rewrite this as e to the y equal to e to the natural log of x, which is really just e to the y equal to x. By the way, you can totally skip this intermediate step here. We know that if y equals log base e of x, that's the same thing as e to the y equal to the x, or equal to x, not the x. And then to find y prime, we differentiated both sides. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. The derivative of x is just 1. And then y prime equals 1 over e to the y, but e to the y is equal to x. So y prime equals 1 over x. So the derivative of the natural log of x, as we know, is 1 over x. The reason I bring this up is because we find the derivative of the arctangent or the inverse tangent in the same sort of way. So yeah, and we got, I'm gonna try and do this kind of thing. So here's what y equal to the tangent of x looks like, if you recall. It's got some vertical asymptotes. It's actually got a lot of vertical asymptotes, right? Like an infinite number of vertical asymptotes, but the ones we kind of look at the most are the ones at pi over 2 and negative pi over 2. And then you do get vertical asymptotes every pi. So there's another vertical asymptote over here at 3 pi over 2, and so on. And the graph looks like this. And it intersects the x-axis at 0 and pi and negative pi over here. And so on and so on and so on. And as you might notice, as you may, maybe not, I don't know, this function fails to pass the horizontal line test. If you draw a horizontal line, it's going to cross the function a lot of times, like infinite number of times. To pass the horizontal line test, we need a horizontal line to only cross the function once. And the reason we need to pass the horizontal line test is for the function to have an inverse. Because if you switch x and y here, you're not going to get a function. In fact, I can't, well, I could draw it, but it's easier to just show you. So, right, here's good old y equal to tangent of x, looking lovely as it does. And here's the inverse relationship. That's not a function, that's a problem. And the way we solve this problem is by restricting the domain of tangents. So if we restrict the domain to just this section here, then when we reflect that around the line y equals x, when we switch x and y, we get this lovely looking thing here. Which is the inverse tangent of x or the arctangent of x. Either name / notation is perfectly acceptable. And instead of having vertical asymptotes at pi over 2 and negative pi over 2, it's going to have horizontal asymptotes at negative pi over 2 and pi over 2. And if you prefer a nicer picture, we can totally look at Desmos again for a second. Instead of this thing here, we're just going to have this thing here. I prefer writing arctangent because it's easier in Desmos to write that. And there's just the arctangent, not the whole thing. And you can even graph the asymptotes if you want. There's your asymptotes. Great. Also worth knowing, it does occasionally come up. Someone might someday ask you, what's the limit as x goes to infinity of the arctangent of x? And that's when it's really good to be like, oh, I know what the graph of that looks like. As x gets larger and larger, oh, you can't see what I'm writing. Sorry, I always make that mistake. If you can't see the thing I'm writing, please let me know. Right? as x goes to infinity, the arctangent function just gets closer and closer and closer and closer to pi over 2. That does occasionally come up in the future. So everyone's like, what was that thing again? Oh, yeah, so this is what the arctangent function looks like. And the way we find its derivative is the same sort of way we found the derivative of the natural log of x. So I want to find the derivative of the inverse tangent of x. But I don't know how. So just like with the natural log, I'm going to rewrite it using the inverse relationship. So I'm going to write y equal to the inverse tangent of x. But then I'm going to rewrite that as tangent of y equal to x. In case that's not clear, the way the inverse tangent function is defined, it's literally defined as the function that undoes what tangent does. So tangent of, for example, pi over 4 is equal to 1. And the inverse tangent of 1 is equal to pi over 4. And that's also true for other values, like tangent of, I don't know, negative pi over 6 is equal to negative root 3 over 3. That's the equivalent to saying the inverse tangent of negative root 3 over 3 is equal to negative pi over 6. When I see inverse tangent, the words I say in my head are, oh, inverse tangent of some number is the angle that if I took tangent of that angle, I know it's a lot of words, we would get the number. Or more easily written, this. If y equals inverse tangent of x, well, inverse tangent of x should be the angle y. And if we take tangent of that angle, we get the number we're trying to take the inverse tangent of. So that's the whole relationship. You don't really need to know all that to take the derivative, but it's good to know what the function is we're talking about. So now I'm going to differentiate both sides of this equation. And just like the derivative of the the derivative of e to the stuff is e to the stuff times the derivative of the stuff, the derivative of tangent of some stuff is going to be secant squared of the stuff times the derivative of the stuff. And it's equal to the derivative of x, which is 1. And now, just like before, we're going to try and solve for y prime. Well, that's not so terrible, at least as far as dividing, right? Y prime can be 1 over secant squared of 4. And now is where you need to know some trigonometry stuff. There's an easy way of doing this, and there's a slightly harder way of doing this. You might know my favorite trig identity. You might not, but I'm going to tell it to you. Student told me this one time, prepare to never forget something you're about to hear. You will never forget this, I promise you. Yeah, James, that doesn't seem very memorable. Well, wait till I say these words. I tan and get sexy. Oh, you will never forget that. It's impossible to forget. I have never forgotten. I've tried to forget it. It's not forgettable. So 1 plus tangent squared of y equals secant squared of y. I tan and get sexy. So secant squared of y is equal to 1 plus tangent squared of y. But we know that tangent of y is equal to x. So that's really just 1 over 1 plus x squared. Or 1 over x squared plus 1, whichever way you want to write it. They're the same. Now, this is not the way I usually do this. The way I usually do this is the following. I think about the fact that tangent of y equal to x over 1. Tangent is the opposite over adjacent. So if I draw a right triangle where the angle is y and the opposite is x and the adjacent is 1, then this other side, if you use the Pythagorean theorem, ends up being the square root of 1 plus x squared. It's true. Right, because this squared plus this squared should equal that squared, and 1 squared plus x squared equals the square root of 1 plus x squared squared. And then if I want to find secant of y, I never remember what secant is. I definitely remember what cosine is. Cosine is adjacent over hypotenuse. Secant is the reciprocal of that. Secant is hypotenuse over adjacent, which is just the square root of 1 plus x squared over 1. And then secant squared is that thing squared. Oh, look, secant squared of y is exactly 1 plus x squared, which is exactly what we're getting in the denominator. Either way you want to get there is fine. I just thought I should show you both those. Long story, very short. The thing you need to remember is that the derivative, whoops, it's all right, of the inverse tangent of x is equal to 1 over 1 plus x squared. Or if you prefer, you might write it as 1 over x squared plus 1. That's kind of the whole thing. And then, of course, just like any function we know how to differentiate, we then throw the chain rule at it. So you might be like, okay, well, fine, James, what's the derivative of the inverse tangent of x to the 6th? You'd be like, okay, well, the inverse tangent of x is 1 over 1 plus x squared. The derivative inverse tangent of some stuff is 1 over 1 plus the stuff squared times the derivative of the stuff. Not too terrible, which is 6x to the 5th over 1 plus x to the 12th. Or you might even make it a little more interesting, say like, what's the derivative of the arc tangent of e to the x times natural log of x? That's kind of gross. It's still just the same rule though. We're going to be like, okay, it's 1 over 1 plus the stuff squared. And then we're going to multiply by the derivative of that stuff. Okay, I have to use the product rule. So the derivative of e to the x natural log of x is the derivative of e to the x, which is e to the x. Leave the natural log of x alone. Plus, then you vice versa, right? You do the e to the x left alone times the derivative of the natural log of x, which is 1 over x. And I probably wouldn't bother trying to simplify that unless someone was making me do it. If I had to do it, I don't want to do it. I would do that. I'm fine. If I had to do it, I'd write it as e to the x times natural log of x plus e to the x over x all over 1 plus e to the 2x times natural log of x quantity squared. That seems awful. I wouldn't probably want to do that, but that's what my simplified answer. I feel like this isn't all the way simplified because I got a fraction and a fraction, but not gonna worry about that. So that's how you differentiate arctangents. Kind of it. And it's kind of weird to me. I'm not really sure why we focus on arctangent in this stuff and none of the other inverse trig functions, but it's true. We only talk about the derivative inverse tangent and like none of the others. They might also mention inverse cotangent. So in case they do, just so you know, the derivative of the inverse cotangent of x is negative 1 over 1 plus x squared. All right. That's all I have to say about inverse tangent, unless you guys have questions about it. Right, we got about 25 minutes left. Let's go ahead and talk about linear approximations, aka linearizations, aka differentials. Probably known by other names as well. Okay, sure. So there's lots of ways to talk about this, but the number one way I like to talk about it is really just as it's really just a tangent line. So when you hear the word linearization, you should just be like, it's not that hard. It's just a tangent line. I know how to find a tangent line. So let's look at this example. Let's use a linear approximation, also known as a linearization, to the function f of x equal to the square root of x at a equal to the a value that we're going to find, or that we're actually the value that we're going to pick if we're not told it, should always be a value that's easy to plug into the function. I'm not going to pick something like 7 because I don't know what the square root of 7 is. I'm going to pick something like 36 because I know what the square root of 36 is. really, well, we'll do this one and then we'll talk more about it. So let's say we have A equal to, sure, 36 to estimate the square root of 38. And here's the idea. Let's see if I can draw this all right. Here is our function y equal to the square root of x, or f of x. I should use f of x, sorry. It's fine. And here is the point that we're finding the tangent line at. So there's 36. There's my tangent line. And the idea is that when we plug in 38, which I'm going to move kind of far away just so you can see the difference here. There's two different things we can calculate. You can either calculate what you actually get when you plug in 38. So that would be the square root of 38. But that's not easy to do without a calculator. Obviously, calculators are pretty easy to get a hold of these days, but you know, we're just pretending like we get. Or you can go up a little bit further and plug 38 into this tangent line that we can easily find the equation of. And instead, calculate what we call the linearization at 38. And what we're going to say is that linearization, that L of 38, is a good approximation of the square root of 38. I think it should be pretty visually easy to see that the further away this number we're approximating is from the number we're using to approximate at, the greater the error is going to be. Right, so this little distance here, that's your error. And if this thing moves further that way, the distance between these two things is going to grow and grow and grow and grow and grow. So typically you're trying to approximate something, approximate a value that's close to the value where we're taking the tangent line at. Okay. So we know how to find the equation of a tangent line. Now, for some reason, there's kind of this very standard way of writing a linearization. I'm still going to start with the usual. My tangent line at the point, I'm going to call it A comma f of A. You could also call it, well, let me just write this down. It's going to be given by the usual equation of a line, right? We know how to find the equation of a line through a point. It's y minus the y coordinate equal to the slope times x minus the x coordinate. But if you have totally forgot, like if you were like doing a linearization, you've totally forgotten what it's supposed to be, just step back and be like, okay, I know it's an equation of a tangent line. Write down the equation of a tangent line, solve for y. So y equals y1 plus the slope times x minus x1. Okay, but y1 is really just the y coordinate of this point. And this point I'm thinking of as A comma f of A. So the y coordinate there is just f of A. And the slope is what? How do we find the slope in calculus? The derivative at the point A. That's going to be f prime of A times x minus the x coordinate, which is just the A value. And instead of calling this y, we call it the linearization. But really, it's just the equation of a tangent line. It's nothing new. It's just a different way of writing it, really. Here's the other thing to be aware of. When you write this, there's almost never a good reason to simplify it. You're going to see this again in 17B or C, I think 17C, with an extra variable when you do functions of two variables. And you're going to find the linearization of a tangent line, a tangent plane to a surface. And it's going to be like the exact same equation with just an extra piece. And I'm going to remind you, don't simplify it. It's much, much easier to deal with this thing if you do not simplify it. Here's what I mean. So for this particular example, our function is the square root of x. Our derivative is 1/2 x to the minus 1/2, or if you prefer, 1 over the quantity 2 root x. And then I'm actually going to plug in my value a, which is 36. So f of a is the square root of 36, which is just 6, which makes sense, right? You plug in 36, oh yeah, you're definitely going to get 6. And f prime of a is 1 over 2 times the square root of 36, which is 1 over 12. So here's what my linearization looks like. L of x, or y, is equal to my f of a, which is 6, plus f prime of a, which is 1/12, times x minus 36. And I really want to make this really clear. Really, really, really. Can I say really more times? Yeah. The slope of this line in this particular example is 1/12. That's the slope of this line. So what we're saying here is if I want to approximate the value of this function at 38, here's what we're going to do. We're going to get 6, and then we're going to add on the rise. Well, we can find the rise, right? We just need to know how far over we go and what the slope is. Because the rise over the run is equal to the slope. Well, look at what we know here. We know the slope is 1/12, and we know the run, right? How much over we go is 2. So the rise, right? How much this part is right here, that's going to just be 2 times 1/12, which is exactly what we're going to get when we plug in 38 right there. We're going to get the slope times how much over we went to figure out how far up we went from that point there to that point there. Okay, so I'm going to, here's what I usually write when I do this kind of problem. I like to say the square root of 38 is approximately the linearization evaluated at 38, which is 6 plus 1/12 times 38 minus 2. I can't emphasize enough. There is no good reason to simplify this. I don't want to know that this is equal to 3 plus 1/12x if you simplify it. It's not helpful. It's really not. Because the whole idea is it's supposed to be 6 plus a little bit. And the little bit's kind of what you more want to focus on. And I wrote the wrong thing there. Sorry, this should be a 36 down to 2. I was doing the subtraction ahead of time. So that's going to be 6 plus 1/12 times 2, which is just 6 plus 1/6. You can leave it like that. You probably should either get a decimal or write it as an improper fraction. So you can either write this as 37/6, although I think it's actually more informative to write it as 6.166 forever. Because that's what 1/6 is, 0.1666 forever. Okay, how close were we? Good question. What is the square root of 38? I don't know. Let's find out. It's 6.1644 approximately. Pretty good answer, right? I mean, actual. So these linearizations give you decent approximations, right? Without a calculator. So if you actually didn't have a calculator, and for some reason you actually had to know what the square root of 38 was about, you could do something like this, and it works. Kind of neat. Yeah. Let's look at a couple more examples. Let's see. Let me see one. Cool. So let's look at this next one. Order here. So put it up later. Let's estimate 1.98 to the 4th power. Oops, you want to see it. So I should mention, unlike the previous problem, I haven't given you anything. I haven't given you a function. I haven't given you an a value. There are things we can find without too much trouble, but we have to look for them. So the whole idea is the function should just be whatever you've got, except replace the number that's in there with x. So if in the previous problem, I had said, just like estimate the square root of 38, I would start off by saying, okay, well, my function is going to be the square root of x. And then I'm going to pick the A value that's closest to the number I've got that's easy to plug in. So for this one, I'd be like, oh, well, the closest number to 38 that I can take the square root of is 36. I should say that I can take the square root of without like using extra tools and get a nice answer. Here, my function is going to be x to the fourth. And what's the prime candidate for my A value here? Right. I mean, it's yelling at us that 2 is the answer, or not the answer, but the point we should be looking at. So we're going to use A equal to 2. I like to write down the formula for the linearization. I know it's L of x equals f of A plus f prime of A times x minus A. But if you don't want to or can't remember that, you can always start with, oh yeah, I know y minus y1 equals the slope times x minus x1. And then y equals y1 plus the slope times x minus x1. And then y1 is f of A, the slope is f prime of A, and x1 is A. It's not too hard to get from there to there if you remember just a couple things. Or you can just memorize this. I will point out the problem with memorizing this, not the problem, but the thing I've seen people have a problem with memorizing this is sometimes they screw up the signs of things. I've definitely seen people write a minus sign here when it should always be a plus. I've definitely seen people write a plus sign here when it should always be a minus. So just be careful if you're going to memorize it. I mean, that could be like my mantra of math. Just be careful. It's easy to make mistakes. Just be careful. So we do need to figure out what f of A and f prime of A are. So I should probably find the derivative, which is 4x cubed. And then f of A is going to be 2 to the fourth, which is 16. And f prime of A is going to be 4 times 2 cubed, which is 32. So my linearization, aka my tangent line, is 16 plus 32 times x minus 2. Again, I want to point out to everybody, you really don't want to simplify this. It is not helpful to know that this is going to be L of x is 16 plus 32x minus 64, which is then negative 48 plus 32x. You really don't want this. Kate, I want to make sure you're seeing this. You really don't want to do this. Because what am I trying to do next? I'm trying to evaluate this thing at 1.98. Right? I'm trying to say, okay, I want to know what's 1.98 to the fourth power. Well, it's approximately my linearization evaluated at 1.98. I don't know what 32 times 1.98 is. That's going to be a lot of work. I'm trying to do less work, not more. If I plug it into this unsimplified version, it's way better. That's going to be 16 plus 32 times 1.98 minus 2. And the whole idea is that whatever the slope is, it's going to be multiplied by something small. This is going to be 16 plus 32 times negative 0.02. That's a lot easier to do the multiplication of. This is going to be 16 minus 32 times 0.02 is going to be 0.64. And we can do that subtraction. That's going to be 15.36. But I can't stress enough, right? Doing this was way, way easier than trying to plug in 1.98 right there. 1.98 times 32 is way more work to do. So I will say once again, don't simplify this linearization. Leave it just like that and then plug in the x value you're trying to approximate the function at. Yeah. I want to say that, right? You could say more, but yeah, great. Okay, let's look at another couple examples. What time is it? Okay, we got 8 minutes. Let's look at one more example. Let's say I want to, yeah, sure. So maybe I want to approximate it's always kind of funky. the natural log of 1.06. So again, same idea. We've got a number, we've got a function. Well, actually, I should say we should find the function. The function is going to be the natural log of x. We might as well write down the derivative because we know we're going to need it. The derivative is 1 over x. And then we're going to find out what we get when we plug in our easy value. What's the easy value we're going to pick? What's close to 1.06? Yeah, 1, right? Our a value is 1. So f of a is natural log of 1, which is 0. And f prime of a is 1 over 1, which is 1. Our linearization here is actually kind of boring. I mean, they're all kind of boring, but this one's extra boring. Our linearization, which is f of a plus f prime of a times x minus a, is going to be f of a, which we found to be 0 plus 1 times x minus 1. So our linearization, I guess we could, okay, we can simplify this one. It's not a crime to simplify this one. Our linearization is just x minus 1. Graphically, right, just in case you're curious, right, here's what's going on. Here's my logarithmic function. It passes to the point 1, 0. It looks kind of like this. And the tangent line at the point 1, 0 is the line y equal to x minus 1. So if we're trying to approximate, say, this at 1.06, we're going to get 1.06 minus 1, which is just 0.06. So the natural log of 1.06 is approximately the linearization at 1.06, which is 1.06 minus 1, which is 0.06. It is a common approximation that the natural log of 1 plus a little bit, small number, is approximately the small number. That's a useful fact that comes up semi-frequently. Yeah, we got time. So usually, if you're trying to estimate something, you're trying to make the function as simple as possible, right? You're going to do the linearization of the function at the point that's the most convenient. But sometimes they're going to give you stuff. For example, here's a homework problem someone sent me that is a little unwieldy, but not that bad. It's find the linearization of f of x equal to the natural log of 8 plus 5x at a equal to 0. Good. If you got to do your test, go to your test. So again, linearization, they're literally just asking you to find the equation of the tangent line. So we're just going to write it down. It's going to be the linearization is f of a plus f prime of a times x minus a. This is not nearly as useful a tangent line, at least not for approximating things. So let's find all the stuff. F of x, we already have. F prime of x is 1 over the stuff. Good luck on your test, by the way. Is 1 over the stuff times the derivative of the stuff. So f of a is the natural log of 8 plus 5 times 0, which is just the natural log of 8. And f prime of a is 1 over 8 plus 0 times 5, which is 5/8. So here's the linearization. It's f of a, which is the natural log of 8, plus f prime of a, which is 5/8, times x minus a, which is 0. So if it is an x minus 0, I would say you should probably take the extra step of simplifying that because it's really a non-step. But this is fine. It's just not very useful because the reason this is not very useful is if you want to approximate, like, say, if I wanted to use this to approximate the natural log of 8 plus 5 times, I don't know, 0.1, which is the natural log of 8.5. In this approximation, I still have to calculate the natural log of 8. So it's not super useful. But you could do this, right? This would be, right, the natural log of 8.5 would be approximately the linearization evaluated at 0.1, because that's what you have to plug in for x to have 8.5 that we're taking the natural log of. And then that would just be the natural log of 8 plus 5/8 times 0.1, which would be the natural log of 8 plus 5/80, I guess, right? 5/8 times 1/10 is 5/80. But usually, if we're doing a linearization, we're trying to do it at a point that is easy to actually evaluate the function at, which this is not, right? It's not easy to evaluate. I mean, it's not easy to know what the value of this function is when you plug in x equals 0 without using a calculator. So just as one last example that we'll use in here, if I was trying to say approximate, what do I want to do here? Let's say, sure, the cube root of, why not, of 70. Well, first of all, we know the function. It's the cube root of x, or maybe x to the 1/3. And what's the closest number that's easy to take the cube root of? Well, if you don't know, just start finding cubic numbers. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 4 times 4 times 4, which is 64, 5 cubed is 5 times 5 is 125. Okay, well, 70 is between these two, and it's clearly closer to 64. So this is the choice you want to make for A. So if it's something like a cube root or a square root or a fourth root, you just take subsequent third powers or whatever your root is until you find the one that's the closest to your value. And you usually want to go one below and one above and then see whichever one's the closer one. So in this case, we'd be like, okay, my A value is going to be 64. My derivative is 1/3 x to the negative 2/3. Or 1/3 times x to the positive 2/3. And then we're just going to throw everything. That'll be fine. I'm going to find f of a, which is the cube root of 64, which is 4. And f prime of a, which is 1/3 times 64 to the 2/3 power. And 64 to the 2/3 power is what? Well, 64 to the 1/3 is 4. That's the cube root of 64. And then 4 squared is 16. And 16 times 3 is 48. This is 1/48. And then we throw the formula at it. Here's that formula once again. Oh yeah, if you got to go, you got to go. At 3 o'clock, I should stop, but I'll just finish this problem. So we're going to have L of x is going to be f of a, which is 4, plus f prime of a, which is 1/48, which I started writing kind of weirdly, times x minus 64. Here's the thing you should notice. The cube root of 70 shouldn't be a whole lot bigger than 4. Right? The cube root of 64 is 4. The cube root of 74 is a little bit bigger than that. This coincides with that, right? If we plug in 70 here, we're going to get 4 plus a little bit more, right? 1/48 times a smallish number here. So if I want to approximate the cube root of 70, L of 70 is going to be 4 plus 1/48 times 70 minus 64, which is 4 plus 6/48, which is 4 plus 1/8, and 1/8 is 0.125, so it's 4. And you could get out a calculator and see what the cube root of 70 actually is and be like, oh yeah, it's pretty close.